Hello, hello, hello. In this worked example, we're going to explore a model for kinetic friction. And we're imagining the sort of situation that you might see where you go to pick up luggage at the airport back in the days where people checked their baggage and maybe even got on airplanes. So there's this rotating conveyor belt, and the top surface of the conveyor belt is moving along at a constant velocity of 1.7 meters per second to the right. And a piece of luggage drops vertically onto the moving conveyor belt. And in order to for the luggage to get up to speed, it has to accelerate. So there's got to be a force that is exerted on the luggage to get it up to this final velocity of 1.7 meters per second. And the question is, how long does it take for our suitcase to get up to speed? And as is usually the case in these sorts of problems, we're going to start by drawing a free body diagram for the suitcase. We'll represent the suitcase by that little dot there. And we'll ask, what are the forces that act on the dot? And as usual, there are sort of two categories. There are contact forces, and the exception is the force of gravity. So let's start by putting the force of gravity. That certainly we know acts in the downward direction, and it has a magnitude of m times g. And then there's a contact force that acts on the mass from the conveyor belt, and we'll call that contact force F sub belt on the mass. And we don't yet know what direction this contact force points in, but it's certainly going to have both a horizontal component and a vertical component. The vertical component is going to be associated with counteracting the gravitational force and keeping the mass at a constant elevation. And then the horizontal component of this contact force is going to be responsible for accelerating the mass and getting it up to speed. And it's conventional to give names for these two components. These are not separate forces that I'm drawing in, they're just components of the force of this contact force that we just drew in. So I'm going to draw them in a different color here. The horizontal component of the contact force, we're going to call F, following Wilson's notation, we're going to call that horizontal component the kinetic friction force. And then we'll call the vertical component here N with an arrow on it. And N stands for normal, which means perpendicular. And this force is perpendicular to the surface of the belt. So that's why it's called the normal force. And of course, the next step is to apply Newton's second law. So we know that the acceleration of our mass is given by the net force on the mass divided by the mass of the mass. And in the vertical direction, which we'll call the y direction, the acceleration is, of course, zero. And that just implies that the magnitude of the downward gravitational force, mg, is equal to the magnitude of the normal force, this normal component of the contact force. So we know the magnitude of N is equal to mg. And to calculate the acceleration in the x direction, well, there's only one thing that has a component in the x direction, and that's this force Fk, which is a magnitude Fk. So I'm going to leave out the vector sign. We don't really need it for a one-dimensional motion. And Fk divided by m. And so far, we haven't made any approximations or assumptions, really, other than the fact that Newton's second law is correct. And now we're going to invoke a model of friction, which is really, as we've said previously in a What's the Big Idea on sliding friction, is really often a pretty crude, almost often lousy model, but we're going to use it nonetheless in this problem. And our model of kinetic friction, And by kinetic friction, again, we mean the friction that exists between two surfaces that are sliding with respect to one another. The model of kinetic friction says that the magnitude of this kinetic friction force is just equal to this coefficient of kinetic friction, this dimensionless quantity, which in this case we're told is equal to 0.3, times the magnitude of the normal force. So just plugging in numbers here, we have 0.3, and the magnitude of the normal force, we argued in this problem, has got to be equal to mg. So with that model in place, the acceleration in the x direction is just equal to 0.3 times mg divided by m. The m's cancel, and we're left with 0.3 g, and that's just 0.3 times 9.8 meters per second squared, and we'll call that 3.3 meters per second squared. So we're just about done. If we know the acceleration, we know the initial horizontal velocity component is 0. The final one is 1.7. The amount of time that it takes to get up to this final speed is just equal to its final speed divided by this acceleration that we just calculated, or 1.7 meters per second divided by 3.3 meters per second squared, and we'll call that 0.5 seconds, which sort of seems like a plausible result if you've ever watched a suitcase fall onto a conveyor belt at the airport. So that's it for this worked example. Hope to see you again soon. Bye-bye.